another additional step, another additional step along with the previous step. So the steps involved while drawing the, while plotting the rapid plotting of root locus were first identify the location of poles and zeros of the loop transfer function. Then we knew that the root locus will start from the poles and inside zeros of the loop transfer function. Then we knew that the root locus is symmetrical about real axis. We also knew that the root locus will never overlap. Then we found out the asymptotes, number of asymptotes, angle of asymptotes, and centroid of asymptotes. Then after that we found breakaway and break-in point. So breakaway always occurs on the real axis between two poles, two real poles. And break-in always occurs on the real axis between two real zeros. Okay. So till this point we did, and we also found out the stability. Fine. We also found out the stability of the system in terms of range of k for which roots lie in the left half, and the range of k for which the roots lie on the right half. So we found the stability of the system by defining the range of k. Then we also proved that part of the root locus is circle. So all those concepts I have defined, rest all is just simple algebra that you can do yourself. I have given the concepts. I have given some numericals through PDF. Please go through that and please solve numericals on your own. So due to time constraints, I'm concentrating more on the concepts. But at the end, I will revisit for the numerical, but do not depend completely on my lecture for numericals. Please solve yourself whenever you get a doubt or difficulty. Don't hesitate to approach me. Fine. So the next part is when the loop transfer function has the complex poles or complex zeros, how the root locus is drawn. Fine. So that is another task we need to solve. So this is one example here. We have a S-plane and we have a complex poles P1 and P2, which has got negative real part and positive imaginary part. Then two zeros at origin and at -1. Okay, two real zeros. So when the poles are complex, we always know that root locus starts from a pole and ends at 0. The same thing is true here also. But the question is how it will start from the pole. So will it start like this? Will it start like this? Will it start like this? So there are infinite possibilities that the branch of the root locus can start from a complex pole. So infinite possibilities obviously is not a right solution. We should exactly know at what particular angle it will start. Then only your root locus is appropriate. So I repeat again, we will have a difficulty when we have a complex pole, because as we know that the branch of the root locus starts from a pole. When there exists a complex pole, we have a possibilities of starting of the root locus. I can show you with another simple diagram here. Suppose imagine we have a S-plane like this. You have a pole here, you have a pole here, and a 0. So in rapid plotting, of course, we need to make approximations, and whatever we draw is actually approximate root locus with certain points keeping in mind. So when I say plot the root locus for this, it's quite confusing. Will it start like this and moves to the 0 inside 0, or will it start like this, or even will it start like this and joins at the break-in point? So there are infinite possibilities to start the root locus. So we have to find some solution for this. At what particular angle it will start. Okay. And at what particular breakaway point it will reach. So we need to find this angle. Okay, we need to find an angle and approximately where our root locus will start. Oh, sorry. Why it is paused? Can you see this, Ganesh?
Yes, sir.
Did you see that whatever I had drawn, or it was
Yes,
paused?
sir. Yes, sir. It was visible.
Okay, fine. So the same thing is true even in the case of a complex 0. So when we have a complex 0 here, obviously the root locus will start and ends at a 0. Ends at a 0. So at what particular angle it will end? At what particular angle it will start. Those are the questions related to complex poles and zero. So for complex pole, the angle at which the root locus starts is called as angle of departure. I repeat again, this additional step is only for the complex poles and complex zeros case. So the angle with which the root locus starts from a complex pole is called as angle of departure, and the angle with which the the root locus starts from a complex zero, or not starts, ends at. Okay, the angle with which the root locus ends is called as angle of arrival. So now we need to study angle of departure and angle of arrival. So there is not much mathematics involved here. One straight direct step where we can substitute and find these parameters. So let me first take up the angle of departure. So for a complex pole, the expression for angle of departure is, okay, it looks like quite complicated as of now. Once you understand how to calculate, it is very much easy. The expression for angle of departure is 180 degree minus sum of the angles of the vectors to a complex pole in question from other poles, minus sum of the angles of vectors to a complex pole in question from other zeros. This is the straightforward expression. Can be written as 180 degree minus summation of poles. Okay, summation of poles means sum of the angles of vectors to a complex pole in question from other poles. That is called as summation of angle of poles. Then minus summation of angle of zeros is sum of the angles of the vector to a complex pole in question from other zeros. So this is angle of departure. So let us see how we can calculate angle of departure for one simple example. So I will make it clear again and again. This additional step is only for the case when we have complex pole and complex zeros. Complex poles and complex zeros, because of the difficulty in guessing the angle with which it starts or the angle with which it ends when it is complex in nature. So consider this example where we have complex conjugate poles +1 and +1 plus j, -1 minus j, -1 plus j, and another pole at origin. So this is an example of two complex pole and one real pole. So we'll start from the first step. How many zeros are present? No zeros. How many poles are present? Three poles. One is -1 plus j, another one is -1 minus j, another is at 0. So P is equal to 3, Z equal to 0. How many number of asymptotes we have? We have P minus Z equal to 3 minus 0, 3 asymptotes. What is the angle of asymptote? Can anyone tell me the angle of asymptote for 3 asymptotes? 60 degree, 180 and 300 degrees, right? 60 degrees, 180 degrees and 300 degrees. Then we need to calculate centroid. Can anyone tell me what is the centroid? It is -2/3. Am I correct?
Yes.
-2/3 because you need to sum up all the finite poles, then minus sum up all the finite zeros divided by P minus Z. So if you sum up all the finite poles, plus j and minus j will cancel. We will have only -1 and -2, which are added to get -2 divided by P minus Z is 3. The centroid is -2/3. Then do we have a breakaway point? So this is a key step for this particular numerical. We know that breakaway occurs on the real axis between two poles. So there is no zero, so no question about breaking, but there is only one real pole on the real axis. So breakaway has to occur between two poles. Since there is no other pole on the real axis, there is only one single pole. So the question of breakaway and break-in is, cancelled. It won't arrive at all. So no need to go for calculation of breakaway or break-in. So one step is reduced. And the next question is, you have drawn already asymptotes, but how do you draw the plot? How do you make the plot is the question. Fine. So for that, we need to calculate angle of departure. With what angle the root locus departs from these complex poles. Then how they follow the asymptotes is the question. So how do they depart? We already know one formula, let us apply it. So I will find the angle of departure for P1. Angle of departure for P1. So now if you look at the expression for angle of departure, to look at the expression or the formula for angle of departure, we have angle of departure equal to 180 minus sum of the angles of the vectors to a complex pole in question. So now our complex pole in question is P1. Okay, P1, and we need to find the angles of the vectors drawn from other poles to P1. Drawn from other poles to P1, and we should add them. Okay. So first let us take this part. First what we'll do, we'll draw the vectors from other poles to the pole in question P1. Then we find their angles, the angles of the vectors. Then we add them. Then this part is completed. Then we'll go for the next part. So let us see how we can do that. So P1 is in question. I am drawing the vectors from other poles. So I am drawing vector from P2 to P1. P1 is the pole in question. And this angle is with respect to real axis obviously. So it is 90 degrees. Then I will draw another vector from P3. I will call this as P3. So P3 to P1 is obviously 130 degrees. So what we need to do now? We need to do 180 minus summation of angles of the vectors from other poles. So there are only two other poles. One pole is in question and these are the vectors. So what is the angle contributed by this vector? It is 90 degrees with respect to real axis. And the angle of this vector is 135. Okay, because it is 90 plus 45, 1 plus 1j. Fine. So now I need to add these two blindly. So that I will write as phi P2 and phi P3. These are the angles of the vectors from other poles. And there is no 0 at all. So no need to draw any vector from 0. No need to draw any vector from 0. So phi P2 is 90 degrees, phi P3 is 135 minus 0 as it is. So we get minus 45 degrees. Minus 45 degrees. So I will call the angle of departure from P1 as phi D1. Therefore, the angle with which my root locus starts or departs from P1 is at minus 45 degrees. And phi D2 is with respect to P2. So when you want to find the angle of departure for P2, the same formula will repeat. That is, now you need to draw vectors from P1 to P2 and P3 to P2. Then find the angles of that P1, which is 270 degree, and for P2 it is 180 plus 45, which is 225 degrees from P3 to P2. So if you do that and calculate the angle, you will end up with minus of its conjugate pole. That is, you will get plus 45. Okay, I have not done the calculation, but the conclusion is that if a complex pole in question gets the angle of departure as phi, its conjugate will always get the angle of departure as minus phi. That's the simple calculation. If you want, you can write and cross verify. Otherwise, you can directly write minus of whatever its conjugate pair had. So these two are the angle of departure for P1, angle of departure for P2. Fine. So how to draw those angle of departure? I will show you now. So let me approximately draw the asymptotes first at 60 degree, at 300 degree and at 180 degree. Okay, let me use different color. So these are the asymptotes we got. Approximately I am drawing. See, this is how our root locus branch follows the asymptote. Okay, so now the question was with what angle it starts. So that is answered by phi D2. So angle of departure for the Second complex pole is plus 45. I have taken a reference line of plus 45 and I have started or departed from the complex pole at 45 degrees. So this is just an approximate graph. How long it will follow the 45-degree line, why it is following only for a shorter duration, all those are irrelevant. Okay, for rapid plotting, what we need is at what angle it starts. So this is 5d. Then what about angle of departure for P1? Angle of departure for P1 is minus 45. So this is 5d1, which is minus 45 degrees. Okay. So I have drawn for only P1 and P2, but for P3 it will follow the third asymptote. It will move towards minus infinity. So the first key point is whether root locus is symmetric. Yes, it is symmetric. Whether it is overlapping anywhere. No, no branch of the root locus are overlapping. Fine. And everything is done with this. Fine. So angle of departure is necessary only to find the approximate angle at which the root locus starts from a complex pole. That's the only thing. So rapid plotting is always approximation. It's not 100% accurate, but we should at least show it is 90%, 95% accurate. So for all this, for showing that 95% accurate, we are doing this circus. So I hope it is clear. Angle of departure, any doubts, clarification? So next is angle of arrival, that is pertaining to complex zero. So if you have a complex zero instead of a complex pole, then how to find angle of arrival? Because the root locus finally arrives and ends at the zeros. So if it is a complex pole, it is angle of arrival. So it is same, similar definition. It is 180-degree minus first summation of angles of vectors to a complex zero in question from other zeros minus sum of the angle of vectors to a complex zero in question from other poles. So this is phi a equals to 180-degree minus summation of phi zeros minus summation of phi poles. While solving the numerical, we will tackle this particular expression. So as of now, the procedure is same, drawing the vector and finding the angle of arrival. Okay, so everyone please write down in your notes briefly steps for root locus. First step, find root locus, find the poles and zeros. Step 1 is find the poles and zeros of the loop transfer function. Second step is just remember that root locus is symmetric about real axis. Root locus starts from pole and ends at 0. Then root locus will never overlap. Just remember these points. And the second step is immediately find the number of asymptotes. Find the number of asymptotes, angle of asymptotes, and centroid. Third step, check whether breakaway and break-in exists. Check whether breakaway and break-in exists. Next, fourth, check whether complex pole exists. Complex pole or complex zero exists. Check whether complex pole or complex zero exists. And in the next line, if there is a pair of complex poles, find the angle of departure. If there is a pair of complex pole, find the angle of departure. Next, if there is a pair of complex zeros, find the angle of arrival. Find the angle of arrival. Okay, so take down a numerical, simplest numerical. Draw the root locus. Sorry. Yeah. Draw the root locus For the following loop transfer function, for the following loop transfer function, and comment on the stability of, and comment on the stability of closed loop system. Comment on the stability of closed loop system. Full stop. Given g of s into h of s equal to, given g of s into h of s equal to numerator k into s plus 2 into s plus 3 in the numerator, s plus 2 into s plus 3 divided by s into s plus 4, divided by s into s plus 4. I repeat, k into s plus 2 into s plus 3 divided by s into s plus 4. So look at the solution on the screen. Don't write anything. We have two poles at 0 and minus 4. We have two zeros approximately at minus 2 and minus 3. Fine. There is no complex pole. There is no complex zero. So capital P equals to 2 and capital Z equals to 2. Okay. So what is the number of asymptotes? It is 0. P minus Z equal to 0. So no asymptote. So when there is no asymptote, no meaning calculating angle of asymptote or centroid. So that step will end at there only. Then next step is step 4. Calculate, step 3 or step 4, calculate breakaway or break-in point. So I have already said breakaway or break-in occurs only between pair of poles or pair of zeros. So let us see. Will there be a breakaway or break-in between these two zeros? No. Okay. There is no possibility of breakaway or break-in. Will there be a breakaway or break-in between these two poles and zeros? This pole and this zero? No, not possible at all. Now, will there be a possibility of break-in between these two zeros? Is the question, because as we have studied, break-in occurs between two zeros. We have to check for break-in between these two zeros. Can anyone say that there exists a break-in between these two zeros? We need to make calculation to confirm that. Fine. But suppose imagine, don't go for calculation, just listen to me. Suppose imagine there is a break-in. There is a break-in, which means two branches will come at this particular point and they will move towards a 0 for one branch and a 0 for another branch moves to another 0. Suppose imagine this is how the root locus are coming and breaking in here. Then now the question is how they are coming. They obviously should come from a pole only, because branch starts from here and ends at zeros. So keeping in mind about the symmetry of the root locus, how you can show a root locus. So can we show some root locus something like this? Is it symmetrical about real axis? No, it's not symmetrical about real axis. So this possibility is wrong. Fine. So this possibility is wrong. Let us look for the another possibility. And second option, that root locus is coming something like this. So this possibility is also not true because it is not symmetrical about real axis. So if you try in any fashion, just in your mind without drawing, if you try in your mind, To verify the symmetrical root locus, assuming there exists a break-in point, we will never end up with the right answer. Okay, we will never end up with the right graph. Instead, the only possibility is root locus starts from the pole and ends at the nearest zero, and the root locus starts from this pole and ends at the nearest zero. So this is the root locus for the system. So let us cross verify in MATLAB. So rapid plotting is more about your imagination and your practice. In conventional plotting, anyhow you can make n number of calculation and denote the points and join them. But in rapid plotting, we need some imagination along with correct understanding. So we'll start verifying in MATLAB. I will type the Laplace function, then I will type the transfer function. So the transfer function should be typed without the cater. So numerator is s plus 2 into s plus 3 divided by s into s plus 4. Am I correct? Fine. So we have s plus 2, s plus 3 divided by s into s plus 4. So root locus of this is so can you see this graph? Ganesh?
Yes, sir.
Fine. So a pole at 0, a pole at minus 4, a 0 at minus 3, a 0 at minus 2. So this is how it starts and ends. Okay. So without actually solving, let us look some more examples. We'll make a calculation in mind and then we will draw the plot. And what about the stability of the previous numerical? Was that asymptotically stable, conditionally stable? It was stable for all k greater than 0. Okay, so the previous numerical was stable for all k greater than 0. So next let us take another example. We have a pole at, let me draw it in the right side. So there is one pole at minus 1, there is one pole at minus 3. So now the question is, please write down the question without fail. Check the closed loop system stability for a given loop transfer function. Okay, check the closed loop system stability for the given loop transfer function using root locus, obviously. So the loop transfer function is g of s into h of s equal to k divided by s plus 1 into s plus 3. I repeat, loop transfer function is gh equal to k divided by s plus 1 into s plus 3. So now let us solve this particular example. So first step, identify the number of poles. There are two poles at minus 1 and minus 3. There are no zeros that equal to 0. How many number of asymptotes exist?
2.
Two asymptotes, fine. That's correct. And what is the angle of asymptote? Angle of asymptotes?
90 to 70.
90 and 270. What is the centroid?
Minus
Minus
2.
2.
It is minus 2. So let me mark the centroid here. and I need to draw two lines with 90° and minus 270°, sorry, plus 270° to indicate the asymptote at the center. Fine. So this is 90° line, this is 270° line, two asymptotes. Fine. Will there be a breakaway point is the next question. So the answer for this is yes, there will be a breakaway point because there are two poles between which a breakaway point can occur. Will there be a breaking point? No, there cannot be any breaking point because there exist only poles, no zeros. So what is the breakaway point? How do you find breakaway point? Please write down in your notebook. We have to find dk by ds equal to 0. You have to find or solve for dk by ds equal to 0. Please solve it for dk by ds equal to 0 and tell me the breakaway point.
S equal to minus 2.
Breakaway point is equal to minus 2. Yes, anybody got the breakaway point as minus 2? Anybody else? I'll wait for one more person to answer.
Yes, sir.
Okay, so breakaway is minus 2. So this is breakaway here. Now we will draw the root locus. The root locus starts from here and one branch follows parallel to the one asymptote. Then another branch will start from another pole, breaks at the breakaway and follows the other asymptote. So this is one branch, this is one branch, this is another branch. Fine. So this is our root locus. So it will go up to infinity and it will stay in LHS of the S plane. The system is asymptotically stable. System is asymptotically stable. Fine. So there is no complex pole or complex zero. So no need to worry about this. Fine. Any doubts in the numerical? Okay, I hope there is no doubt. And we'll take up the last one. So we have a pole at say plus 2 and plus 3 and zeros at minus 2 and minus 3. First question, will the root locus be a circle? Whether root locus is circle, I can tell it directly.
Yes, sir.
Yes, root locus is circle because see, there exists one breakaway, there exists one break-in. Okay, so the root locus has to start from one of the pole and break here, and it has to follow the branch in this fashion because it has to find one friend who is already waiting to end, and the another branch will start from another pole. Okay, and it will break at this point, and another friend is waiting to finish off this branch of root locus. So this is obviously you will end up with a circular root locus. So just remember the combination of position of poles and zeros. So there are two poles, two zeros, no asymptotes. There exists breakaway, both break-in and breakaway. So you can find breakaway and break-in just by differentiating dk by ds. You will get 2 points after differentiating. Out of those 2 points, whichever lies between poles is a breakaway, whichever lies between 0 is break-in. Fine. Then the common question is comment on the stability. So this system is conditionally stable. This system is conditionally stable, and we already know that how to find gain k or the value of omega at this intersection with the imaginary axis. Fine. So that everyone knows how to find this. We have to equate this to, we have to equate s to j omega. Okay, substitute s equal to j omega in the loop transfer function. Then find its characteristic equation, equate it to 0, and separate out real and imaginary terms. Then you will get the value of k and omega. So for value k greater than whatever you get, the system root locus lies in the LHS, therefore system is stable. Fine. So I'll show that on the MATLAB now. So we have s equal to tf of g equals to s minus 1, s plus 2 star s plus 3 divided by s minus 2 star s minus 3. S minus 2 star s minus 3. Fine. This was our transfer function. So if you draw root locus, you will get g equals root locus of g, and you can look at the graph. So this is actually a circle. Fine. The root locus starts from here. I'll move the cursor on the blue color line. So look at the k again. Gain is increasing, gain is increasing, gain is increasing. So when it intersects with the imaginary axis, our characteristic pole or the characteristic root has a 0 real part and a negative imaginary part, which is minus 2.45. So at gain k equal to 1, the characteristic root is moving towards the left half. So for any value gain k greater than 1, our characteristic root will move to the left half. So the same is true for conjugate pair also. So for conjugate pair also, at k equal to 1 approximately, we have a imaginary characteristic root. And for k greater than 1, the characteristic moves to the left half. The system is stable for k greater than 1 is your comment. This is a conditional stable system. Fine. So take down the answer for this numerical, solve and cross verify. Stability, yeah, tell me.
So here in the root locus, it's starting from +2 and ending at -3.
Yes.
The green color. So
Yeah.
in the
Diagram
diagram,
it was different.
yes, sir.
Yeah,
So-
don't worry about this actually. Where exactly ends it is not required for us.
Okay, sir.
Okay, because this is a rapid plotting. We only need the shape and the approximate values of parameters. So let it end at any 0. Let it start from any pole. That doesn't matter. You will get full marks for that.
Okay, sir.
Okay. Because it is very difficult. Only with the knowledge of these things, we cannot make out where exactly it ends.
Okay, sir.
Fine. So is it clear? So we'll continue with a few more numericals in the next class. And please do solve the numerical. Please do solve the numerical. Okay, thank you. One and all.